Okay, here's an example of using a Laplace transform approach to find the transfer function for a circuit. Okay, in this circuit we have an input voltage Vin and an output voltage measured across the capacitor Vout. So it's a simple series circuit. Okay, so we're going to find first of all the transfer function Vout over Vin, and then we're going to convert this to an ODE. All right, so let's get started. All right, so first of all, I'm going to redraw this, and I'm going to put down everything in the Laplace domain instead of the time domain. Okay, so in this case, one thing that you should know is that if you want the transfer function of a system, you can put in an impulse function. Okay, we've talked about that before, and get the output for that input function. Well, if you take the Laplace transform of a delta function, you get just simply a 1. All right, so we can replace Vn with 1 since we're looking for a transfer function. Okay, if we were looking for the unit step response, you'd put 1 over S. Okay, so, and then resistors stay resistors, so that's an R, and then a capacitor becomes, instead of just the C, it's 1 over CS. Okay, so at this point, here's our output, V out of S. Okay, so this looks pretty simple. This is a very simple circuit. What we can do is we could find the current. Going back to your circuit days, if you found the current of a series circuit, then the voltage V out of S would be 1 over CS times I, the current I. Okay, well, the current I is pretty easy because we can write voltage equations and Ohm's law. Okay, so I'm going to go in a loop in this direction. I'm going to write the rises and the drops using Ohm's law. Okay, so when I go in this direction, I have a rise of 1 volt, and then the drop would be I times R, and another drop would be I times 1 over CS. Okay, so at this point, I should be able to solve for I. Okay, so factoring out I get R plus 1 over CS, and I can solve for solve for I. Okay, I can multiply the top and the bottom by CS to simplify the algebra a little bit, and that's what we get for the current I. All right, so then our voltage output, okay, would be V out is equal to I times 1 over CS. So I notice that the CS cancels, and I get 1 plus RC S plus 1. Okay, and here's another circuit we don't need. Let me delete that. Okay. It's common to write a transfer function where the coefficient in front of the denominator, the highest power of S in the denominator, is a 1. So I could do that, and I'm going to substitute back in V out over Vn, because that's the transfer function. Remember, we used the trick where I plugged in an impulse function and found H of S, but once I do that, that's the overall transfer function. So that's a trick for you. Substitute for Vn, you substitute 1, okay, and then your transfer function just falls right out. Okay, so using that trick, we have 1 over, and I'm going to factor out the RC, and I would get an S plus 1 over RC. Okay, and so I could write this in this form, 1 over RC divided by S plus 1 over RC, right? So this is be a first order pole, okay, where S is equal to minus 1 over RC is the pole location. Okay, so that's a quick example. I'll do a few more for you as well. So there you have a quick example of applying a Laplace transform theory to analyzing a circuit and writing the equations. Okay, so that's the answer for part A. Okay, so that's the answer for part A. All right, for part B, we're going to take our transfer function, and we know that V out over V in is 1 over RC over S plus 1 over RC. All right, so I can multiply both sides by V in. And then move the denominator, multiply by the denominator, so S plus 1 over RC on both sides. And I would get V out S plus 1 over RC is equal to, these cancel, 1 over RC V in. Okay, all these were Laplace variables. Okay, so to convert that to an ODE, anytime I see, I distribute this through, and this would be V0 times S, so that would mean in the time domain, because it's multiplied by S, it's a derivative. Okay, so that's the differential equation for this circuit. Okay, so there's a quick example for how you apply a circuit analysis technique to come up with a model for a circuit.